All right, welcome to video number 5 on Lambda Calculus. Last time we had stopped, we had covered substitutions. Okay, very important concept. Basically, the process which happens when a function is called. Okay, when the formal parameter gets the value from the actual parameter. Okay, and the body of the function is replaced by a new version of the body in which the formal parameter is replaced by the actual parameter. And there was one situation where, based on the scoping rules and the bound and the free variables, there was a situation where we had to be careful, and that was the capture case. Okay, that is, if the bound variable in the function in which you're trying to replace happens to be free in the new value. Okay, then when you blindly replace, you have an unintended consequence of making a change to the semantics of the program which you're trying to execute. Okay, so it's like a programmer writing one function. Okay, and then when the compiler generates a code, it runs some other function. That will be terrible if that's how compilers are written, right? Anyway, so that's the concept of substitutions, and we saw that, and we're going to see a few more. I mean, even in the beta reduction, the last concept, substitution is used. So we'll see some more examples of substitutions. Okay, now we are at the final concept, and that of beta reduction. Okay, so this is basically an operation which defines the semantics of functional programs or Lambda calculus, and it's basically tells you what to do when you're given a big expression, what to do and how to resolve the function applications. So this focus of beta reduction is function applications. All right. So given a function and an actual parameter or an argument, what happens when we apply the actual argument, or when you apply a function to an argument? Okay. That's what beta reduction is all about. Okay, so which means that we have to have an apply function application term, and the left side of that application term must be a function lambda term, and the right side could be anything, right? So or if you had m must be a lambda term, and n must be anything. Okay, or m is a function term, but lambda term, and n could be anything. Yeah. Okay, but let's quickly motivate this and then get to the formal definition. Consider the lambda term lambda x dot x square, the times xx. Okay, so this is the thing we have seen before, and this denotes the square function, right? It's an anonymous function. Everything in lambda calculus is anonymous. No names are given. Okay, to call this function with argument phi, all we do is we construct the apply term in which we put the function here, and then we put the actual argument there, okay, next to each other, and then put parentheses around them. So that's how you call a function. Okay, got it? So when you have such a thing, such a term like this, where there's a function and then an argument sitting next to it, beta reduction is applicable. Okay, so beta reduction is applicable only in this situation. Okay, so you must look for a subterm which has a application with a function here and something next to it. Okay, so beta reduction allows us to execute this function call. And what do? We substitute, okay, because we have to do a substitution, formal parameter with the actual value, right? So we substitute the bound variable x, okay, so we substitute this x, which is the bound variable, with 5, okay, so you have to read this sentence very carefully. We substitute the bound variable x of the function abstraction, which is this one here on the left side, with 5, okay, so we are substituting x by 5, where, I mean, you cannot just substitute in thin air, right? You have to substitute somewhere, okay, where in the body of this function, in the times xx, okay, which is the body. Okay, got it? So this is how we write this beta reduction as. So this whole paragraph which I just read in English, okay, we or not in particular this particular sentence, okay, we substitute up to this point. Yeah, that sentence that is the essence of beta reduction. Okay, so but for the beta reduction to happen, you must have a term in a particular format in this particular format. Okay, only then you can apply a beta reduction. Okay, the format is application, and obviously the left side of the application must be a function term, a lambda term. Okay, so that's very particular. Okay, and we do have it here in this situation. So we can apply a beta reduction. So we say equal beta means this is reduced to this. Okay, now I show it in 2 steps. Okay, or actually in this case 3 steps, but there is only 2 steps. Okay, what you do is you take the body, okay, of this function, which is times xx. That's the body. Okay, and put that here. That's a term in which we are going to make substitution, and we put the square bracket and we put x here, and this x is the same as the variable next to the lambda. Okay, so we are going to replace x, and then what you write to the right of this equal to is whatever term is sitting here. Okay, so it happens to be 5, so we say, so we're going to substitute x with 5 in times xx. Okay, so that's the beta reduction. Okay, and of course we did not see the rule for times, but the times rule works the same as the apply. Okay, so you have to apply this substitution in this and apply the substitution in that, and then we have to combine the two, place the answers next to each other, and then keep the left parenthesis and then the times there. Okay, so that's what you get here, left parenthesis times, then the x is replaced by 5, x is replaced by 5, and the right parenthesis. So this is the answer you get when you make the beta reduction. Okay, got it? So this term reduces to this term. Okay, reduces or transformed or rewritten, whatever. There are many ways you can say this. Okay, so you start with a lambda term, and then you identify a beta reduction inside that. Okay, and then you apply the beta reduction, and you get a new lambda term. Okay. Now, of course, this lambda term, if you want to do anything further with this, there's no lambda beta reduction you can do on this. Why? Because you don't have the function application. Okay, so that's why you will probably go to arithmetic operations times 5, and you probably will have 25 out of that. Okay, but this part is not critical in understanding the beta reduction. Okay, this part is important to understand the beta reduction. Okay. Now, by the way, again, I'm emphasizing it again. The beta reduction can be applied only to a lambda term of the form lambda x dot m followed by n. Okay, that's the only term you can apply beta reductions to. Okay, got it? Now, also the note basically talks about the impure. Okay, so if there is impure times 5 kind of thing, what do you do? It's easy to extend the definition of substitution for that. Okay, we don't do that, but it's pretty straightforward. Actually, it works the same as the function application mn. That's exactly what you do. Okay, so maybe if time permits, I may go back to the slides and add the rule for that. Okay, not very critical. Okay, all right. Now the previous slide was just an example, right? But now we formalize it. Okay, we make it very formal. And here's the formula. Very simple. Okay, one line. Okay, with the formal definition of a beta reduction. So if you had a term of this type, lambda term of this type, why? You must have that type. Okay, if you had some other type or some other format, it will not work. Okay, so this is a prerequisite for a beta reduction to happen. Okay, if you had, and we do have that term, right? A lambda term here and an n here, and then that's a actual parameter, and the x is the formal parameter. So you can see that we say that this is equal to beta reduction, beta equivalent to m. So basically, the lambda x vanishes, and this n also vanishes. Everything vanishes. Only m survives. Okay, only the body is left. Okay, but in the body we have to make a substitution. Okay, we have to substitute x by n. X is the formal parameter, n is the actual. Okay, so x is the formal parameter, n is the actual parameter. Okay, so that's the substitution we make in m. It all falls in place, right? So exactly what we saw in that example of the is prime while earlier. Okay, all right. This term is referred to as a beta redux. Okay, so when it's ready to be reduced, the term is called a beta redux. Okay, and the result, which is on the right side here, is called a reduct. Okay, reduct. That's just names given. So the left side, this thing is a beta redux, and this is a beta reduct, or just a reduct. Okay. Now, of course, we understood how to do this once, okay, one time, okay, one time. Now, in general, this process is repeated again and again and again and again and again, okay. So in general, the way Lambda Calculus compiler or interpreter will work is that you're given probably a very long lambda expression, okay, lambda term, okay, very long term. Maybe it goes into 2-3 pages or something like that. I don't know. It depends on how big programs you write, okay, right? Anyway, Lambda Calculus is a programming language. Don't forget that, okay? So if you want to write a program to find the prime numbers, the program will be, in Lambda Calculus, it will be quite big, okay? Anyway, what is given to us is a lambda term, and we want to identify a beta reduct inside this, a beta redux inside this, okay? And if you find one, you apply the beta redux on that portion, okay, not on the whole thing, but just on that portion, and that portion gets transformed, and you get a new. But the rest of the pieces are kept as it is, so you get a new lambda term after the beta. You actually get a beta reduct, okay. Then on the beta reduct, you try to identify another beta redux. If you find one, you apply beta reduction on that and get another beta reduct, okay, so you'll get a third term. So you're actually starting with one term and modifying it and getting another term, and then on that you're doing a beta reduction, you get another term, and so on. Now, by the way, you do this sequentially, so you don't go ahead and apply the second beta reduct on the first original term, okay. You had to apply it only on the second term which you got, okay. So it's a process of starting and then modifying that the lambda term again and again and again, okay, until you reach a point where there are two possible endings to this process. One is that you don't find any beta reduxes anymore, okay. That's a good result in some sense, see, because you have the final answer, okay. So whatever final lambda term, that is the final answer, okay. Hopefully it's the right one you're looking for, okay. But who knows, right? That's true even for programs, okay. You guys are going to do that in my assignments, okay. Who knows what your programs, when you submit your assignments, what they're going to do, okay, right? If they do what they're supposed to do, you get 100. If they do something else, you get 90, 80, 70, or whatever, 0 or something like that, okay. Same thing with the Lambda Calculus programs, okay. So at the end, what you get is what you started with, right? Garbage in, garbage out. You must have heard of that, you see, or good things in, good things out, okay. Anyway, that's a process. So the beta reduction is we define it one time, but we apply it any number of times, okay. And we're going to see some examples, okay. And finally, a term which doesn't have any beta reduxes, okay, no more beta reduxes, okay. That's supposed to be in beta normal form, okay. So here we have three terms: beta redux, beta reduct, and beta normal form, okay. Beta redux is a term which looks like this, okay. So that's the beta redux, and after applying this, this is the beta reduct, okay. And the beta normal form is a term in which there is no beta reduxes, okay. That's all, okay. So those are the three terms, and of course that's the ending point of a execution of a program, a beta normal form, okay. All right, so let's do. We are doing an example now, not just of one beta reduction, but multiple. Okay, so this is given a program. How do you end up? Okay, how do you run the program? Okay, so a program in Lambda Calculus is run by applying beta redux again and again and again. Okay, until you reach the normal form. Okay. Okay, I think in this slide there are 3 examples. Okay. The first example is only one beta reduct, and actually we stop. Okay, so it's also complete, but it happens only once, the beta reduction. So what we have here is, this is the term. Okay, lambda x dot y, and then lambda z dot zz. Okay, so it's a product or application, and this term here is a beta redux. Why? Because it contains application, and on the left side of the application is a function lambda x dot y, and the argument is lambda z dot zz. Okay, so that's the actual argument, and then the formal argument is x, and then the body is y. Okay, So this looks in the beta redox form. So what will be the answer? Equals beta. It'll be the body, right? Body, which is the y. In this body, we have to replace x. We are replacing x by this formal actual argument, which is lambda z dot zz. Okay, so that's what the definition says you must do. Okay, so this is equal to that. Now, when you apply this substitution, what do you get? In y, you replace x by something. That's the same as y, right? Because in y there's no x. Okay, so y does not change. So that will be the answer, final answer. So this is one step beta reduction. Okay. And this y doesn't have any beta reduxes, so this is in beta normal form, and you stop there. Okay. There's a second example, also actually applies only one step. Okay. So we have lambda w dot w applied to lambda w dot w. Okay. That's an interesting example. Okay. But interestingly, it is in the beta redux form. Okay. So it is in the form in which you can apply a beta reduction. Okay. And that form is you have a lambda term on the left side and then something on the right side. Okay. So since it's at that form, we have to take the body of this function, which is w, and put it here. And in that body, we have to substitute what? Substitute w, which is the formal parameter, w, by this actual parameter, okay, which is lambda w dot w. So in w, we want to replace w by lambda w dot w, okay. That's also easy, right? W becomes lambda w dot w, okay. And this particular term doesn't have doesn't have a beta redux in it. You see why? Because there's no application here, function application. So that's the final answer there. So there are two examples here in the first two lines. In both of them, we stop as after one application, one beta reduction. Okay. Let's look at the third example. Okay, and here in this box here, okay. We are showing a progression of beta reductions, okay, and on this also we'll show something later on, but let's look at this. Okay, so here's a term which this is a term given to us. Okay, I'm not sure if we have seen this before or not, but that's okay. Okay, but this, if you parse it out and look at the parentheses, it looks like this applied to this whole thing, correct? So there's one application there. And then this whole thing is actually nothing but this applied to this. Okay? So there are three applies, actually more than three applies. There's an apply here between this z and that z also. Yeah. But if you don't consider that, there are three applies at the top level. Okay? So there is a term here, or if you want, I can use this pencil here. Oops. Okay. And last time we did that, and that got rid of everything. Yeah, that's right. So if you look at the, this is one term, which is applied to this term till that, right? So that's the outer application, and the inner application happens this term to this term. Got it? I hate it. Okay. Let's see if I can just erase this part. Okay, I go back to this one. Oh, that gets there. Okay, keep that here. Maybe I'll be careful. Okay, I have the eraser on. So we have two applications, and so in some sense there are two beta reduxes here, correct? So one beta redux is okay. Maybe I'll take this out. So you understood the three terms there, right? Okay, I'm going to take this off. Okay. So one beta redux is with this as the function and this as the argument. Okay. The other beta redux is this as the function and this as the argument. Got it? So we have two beta reduxes in this particular term. Okay. Now we didn't encounter this situation before, but this is the first time we are seeing a lambda term in which there are two beta reduxes. Okay, and the way to proceed with this is you can choose either one. Okay, and there's a fantastic theorem back in 1930. Okay, it's called the Church-Rosser theorem. Okay, Rosser was another PhD student. Okay, by the way, Church was a genius. He had geniuses for his PhD students. Okay, one of them was Turing. We said that, right? The other was Rosser, R-O-S-S-E-R. And Church and Rosser came up with this property, which is a very important property theorem, which says that the order in which you pick, in which you do the beta reductions does not matter. Fantastic, right? So if the order mattered, then we need to know what order it is. See, so the point is that if you had two beta reduxes, you can choose any one. Okay, there's a choice. Okay, of course, if you choose a particular one, you may have to struggle more to get the final answer. But if you choose another one, you may find the final answer very quickly. Okay, so it all depends on how you do it. Okay, and actually in this case, it depends on your choice. You end up doing more work on one choice and less work on the other choice. Okay. So here I chose to. That's why I shown this part in red. Okay. I chose to focus on the second application, not on the main one. In this first way to do it. Okay. So we are focusing only on that, and we're going to leave the lambda x dot y as it is. So that's why you can see that that's as it is here. So what? How does this beta reduction work here? So we have to replace z by this in zz, correct? So that's how it works. You take the zz, in that you replace z by lambda w dot w. Okay, so that's exactly beta reduction definition I've applied to this piece, and I get that. Okay. Now this is the beta reduction, but then the one more step of the substitution will produce the final answer for this beta reduction. Okay. So in z, we replace z by lambda w dot w. So this z becomes lambda w dot w. This z becomes lambda w dot w. And that's how this substitution produces this result. Okay. All right. So the two lines are the two, yeah, this is the original one. And then the next two lines corresponds to one beta reduction shown in two steps. Okay. A substitution and then the actual substitution happening here. Okay. So we get this. Okay. Next, again, there happens to be two beta reduxes here. Okay, there's one here which is the original one, and the other one is the one which was produced by this ZZ. Okay, here. Okay, between these two. Okay, so again, we chose to do this inside one. Okay, it's your choice. You can choose the outer one or the inner one. Okay, I'm choosing the inner one. Okay, so in the inner one, we had to replace W, which is the body. No, excuse me. We had to replace this W, which is the formula parameter, by lambda w dot w, which is the argument, in w, which is the body, right? So we get the w, the body, and then in that we apply this substitution. And when you apply that substitution, this happens with the same w as this, so you get lambda w dot w. Okay, so that's what you resulting after the two steps of this one beta reduction. Okay, so you get this. Now we have only one function application. So there's no choice here. Okay. So you take this one as the lambda term, and this is as the actual parameter. So in y, you must replace x by lambda w dot w. Okay, so that's what we write here. In y, replace x by lambda w dot w. And this one is easy, it's just y, right? So the final answer for this is, after 3 beta reductions, you get the final answer y. Okay. Don't worry about what y stands for. Okay, maybe y is the magic cure for COVID or whatever it is. Okay, but anyway, after 3 steps, we get the answer there, right? Y. Let's see whether we choose a different order. Okay, so I take the original string and put it here. And now, instead of taking the inner one, I take the outer one. Okay, outer lambda x dot y dot, or whatever the application is, not the dot, but the application on that. Okay, so in this is my lambda, and this is my actual argument. Okay, got it? So this would be in y, replace x by this gargantuan thing, this whole thing. Okay, and you can see that now in y, replace x by something means ignore that and just say y, right? So you can see that if you had chosen the first application, you would have reached the final answer in one beta reduction. Okay, but because you made the wrong choice, not the wrong choice, the longer choice, okay, you chose this one, and again here you had a choice between those two. Again, you went to the second one. That's why you took 3 beta reductions before you reached y. Okay. Now in the second step, if you had chosen the first application, you might have reached y in 2 steps. Okay. So this is a good example where there are multiple choices of reduxes, and then depending on the choice, you may take longer or shorter time to reach the final answer. Okay. Now, this is the Church-Rosser theorem, by the way. Okay, so this statement here. Okay, and that theorem says that the order of applying beta reductions is not significant. The end result is the same, especially if it terminates. That is, if all the reductions, all the sequences terminates. Okay, then the end result is the same. So it's a very important theorem. It is something which they had to prove before the lambda calculus could become practical. Okay, that's a good example here. The third example. The first two are one step, and so it's not very too much fun. Okay. All right. So now what we do is we actually do the same examples, I guess, or something similar. No, it's the same example. Yeah. So I take the first example here, lambda x, that first example, and put it here, and then I've shown the same line. Okay, I've taken this line, the first line here, and shown it in the next slide. Okay, here in the first line. I'm going to show you how to do this using the expression trees. It becomes a little bit more visual, and it looks, I mean, it's more writing, more drawing, but actually it becomes much clearer. Okay. And I would encourage you to do this tree on some of these problems. Okay, it's a little tedious, but also it's very tedious to deal with these parentheses in all of these. Okay, if you're good at identifying the start and the end parentheses, you'll be good at this. Okay, applying beta reductions. Okay, I'm going to teach you how to do the tree beta reductions in trees. Okay, nothing new here, the same concept. Okay, just visualization. Okay, so you take this original term and make a tree out of it. Okay, so and that's a tree without these boxes. Okay, without all this other writing, just a tree. Okay, you can see that it's an application on the top, right? So that's why we have an apply. On the left side we have the lambda x dot y. You had a lambda x dot y. Okay, on the right side we have lambda z dot zz, which is lambda z here. Zz is apply zz, right? So that's how you construct the tree for this. Okay, it's a small tree, so it's easy to see this tree corresponds to that expression. Okay. Now let's look at, forget about the expression now. Now you're looking at the tree. Okay. So in the tree, your job is to identify a beta redux. Okay. And the beta redux in the tree is identified by an apply node like that, and a lambda node on the left. Okay. So if you see an apply anywhere in the tree and to the left child of it is a lambda, then you have a beta redux. That's how you identify a beta redux. Okay. Exactly same as you do it on the linear form here. Okay. That's how you identify the beta redux in the lambda term there. Okay. But this is how you visualize it. Okay. So if you can visualize this big tree, I mean this is a small tree. Okay. By the way, there are two applies in this tree. There's an apply here and there's an apply here. Okay. But this apply doesn't have a lambda on the left, correct? It has a z on the left. So this is not ready to be a beta redux. Okay, maybe eventually at some point in time this z might get transformed to a lambda. In that case, this will become a beta redux. Okay, but right now it's not. Okay. So but there is at least a one beta redux on this. Okay, so that's shown here. Okay, in red. Okay. So now you can apply a beta reduction on this. Okay, and the way I show it as follows: I draw boxes around the body. This is the body. Okay. And this, I put a box around this actual argument. Okay, this is the actual argument. Okay, for the apply, which is the second part, right? And the lambda x, this is the formal parameter. Okay, so I write this way. Now you don't have to write all of this. If you know what to do, you can actually do it. So the result of applying beta reduction on this tree would be another tree. Okay, it will be a new tree, and the new tree will contain only the body. Okay, so the three things disappear in this tree. The apply node disappears, the lambda node disappears, and everything to the right child of the apply node disappears. Okay, so a whole bunch of things disappear. The only thing which stays is the body. Okay, the y node. So that stays here, but it doesn't stay as is. You have to apply some kind of substitution in that. Okay, and in this case, the substitution is x is replaced by this whole thing here. This whole tree, the right subtree of apply, is lambda z dot zz. Okay, right? So you substitute x with this in this, okay? And we know what happens there. The y doesn't get changed, right? Because in y you cannot replace x by something, okay? So that's why you get this tree as the answer, and that's all, okay? So in one beta reduction you get that, okay? So this is how you visualize it in a tree. Let's do the second example, okay? This is the second example, okay? Again from that same 2 slides back, okay? This is the second line basically from there, and this is the tree for that. Apply lambda w dot w is the left side, and lambda w dot w is also the right side, okay? So it is lambda w dot w applied to lambda w dot w, okay? So again in this you look for apply and lambda, okay? And you see a beta redux here, okay? So again in w replace w, okay? So in this case some real replacement will happen, okay? By lambda w dot w, which is this right subtree, okay? So what will happen is that this w will get replaced by this tree, okay? Lambda w, and everything vanishes. The lambda node vanishes, the apply node vanishes, the right subtree vanishes, and this subtree stays, but it gets modified by when this w gets replaced by that. So when this node gets replaced by that, you would get lambda w, that tree, okay? So that's visually, if you want to see the same, and that's the answer here, okay? These things make a little bit more sense when you have multiple beta reductions. So this is the third example. Again, the long way to y, okay? Not the short way to y, okay? The short way to y is actually shown below here, okay? So you start with this. The green apply is what is shown here, okay, below. So if you chose this apply rather than this apply, okay? By the way, if you look at this original tree for the big expression there, okay, there are 2 beta reduxes, okay, the apply lambda x and the apply lambda z, okay. Those are the only 2 beta reduxes, and unfortunately in the first attempt we tried the lower beta reduction, the apply lambda z, and that's why we ended up 3-4 steps here, okay. But if you had chosen the first higher one, apply lambda x, then you would have gotten in this y replace x by this whole tree, but then there's no x here, so that's why you end up with y immediately, okay, in one step, okay. But if you go laboriously making the wrong choices of the beta reduxes, you'd go from here to here, so you can actually see the outer tree, the tree which apply lambda xy, that remains the same here, lambda xy, you see. But because this is the beta reduction, these 2 nodes disappear, and in the body, which is the apply zz, we replace z by lambda ww. So that's why you get apply. This is the old z and the lambda ww, and this is the old z which is sitting next to that, okay. So the body apply zz survives, okay, and becomes the right child of this big outer apply, and you get this tree here, okay. And in this, again, we had 2 choices of beta reduxes, and again we make the wrong choice. Now if you made the right choice and chose the top one, you can end up below in one step from here to y, okay. I should have shown that, but maybe I should put that in green and then show that below. But you understand what will happen there. But if you made the wrong choice here, so in this w we replace w by lambda ww. So that's why you get lambda ww here in this whole apply, okay. And then the final step is we finally get to that top apply, okay, and that's when you replace in y, replace x by this, you get y, okay. So this is the long way to get y. This is the shortest way to get y. There's a shorter, little bit in between way to get to y, and that is from the in between tree apply the higher apply, the higher redux, okay. Then you can get a y here immediately, you see. That's a good example because there are 3 different ways to get to y. One is the quickest way, one is the longest way, and there's one intermediate way, okay. From here you can get to y, okay, in one step, okay. So this is another way to actually solve some of these problems using trees, okay. Okay, I guess we got maybe there's only 3 more slides, so I will may go a little bit beyond 34-35 minutes on this one, okay. So this will be the final video for this, okay. I may augment some lambda calculus videos on some homeworks and so on, okay. Now here's an example which uses the notation from my interpreter, okay, lambda x, okay. Lambda x times xx and then the 2, so we are finding 2 square here, okay. Now, if you did that, so there's a beta reduction here, lambda x and the 2 there. So you replace x by 2 in times xx, so you'll get times 2, 2, and that can evaluate to 4. And in the tree form, you take the original expression. Oh, by the way, I call it app instead of apply. Doesn't matter, the same thing, okay? App, and then on the left side is the lambda x times xx, okay? And the right side is the 2, the formal parameter, the actual parameter. And with one beta reduction, inside this body, which is the time xx, we replace x by 2, which is what we get here, times 2, 2. And this can be calculated using not beta reduction. By the way, the second arrow is not beta reduction. It's just a math calculation on this to get 4, okay? That's using a different notation for lambda calculus, okay? Here's, oh, maybe I do need a video, yeah, because this is a higher order function, okay? Okay, so let's stop here and we'll come back and do another 6th video on this, because I think that's a little bit detail on this higher order function which I want to discuss, okay? Okay, we stop here and we'll come back one last time on lambda calculus, okay, on the 6th video.